Welcome to Jumping and Not Hitting the Ground, High Altitude Flight, Topic 6. Last topic, we talked about low altitude flight, what we called repelling the Earth. In this case, we're going to learn about the art of falling. Over the next two videos, we will discuss definitions pertinent to this, reference frames and initial orbits, and then in the second video, we'll talk about transfers of orbits and escape from around a celestial body, i.e. Earth. Like all of our lectures, we will start with a cartoon. Take a look at this picture. What do you think it is? What's it taken from? This picture was taken from the Apollo command module as a lunar module descended towards the moon. In this picture is every human being that has ever existed, minus one, the photographer. There were two of these pictures taken in Apollo 10 and Apollo 11. They look distinctly similar, but they are the first of their kind in history. Since then, we've been able, of course, to take pictures of all human beings that have ever lived from our space probes. But how do we do this? How do we get there? So over the next two videos, I want you to ask and answer these questions for yourself. How and why aerospace vehicles fly? Again, we did it last week for flight in the atmosphere. Now we're going to talk about how aerospace vehicles fly when there isn't an atmosphere. How do we define where there's no atmosphere? And is there really no atmosphere? I want you to think about why energy is negative and what happens when it's positive. Now, this won't mean a whole lot to you just yet, but in not too long, we're going to be going through what that means and why we calculate it as negative and the like. And of course, what do you do when you want to hit the ground? Because obviously, most of the time when we go up into space, we want to come back in one way or another. Maybe we want to come back intact, or maybe not intact. So let's start with what do you mean? Definitions. Okay, on this chart, on this table, are a number of definitions that we're going to expect you to start to understand. You'll have these at your hand for a midterm exam or a final exam. So don't worry about memorizing them exactly, but you want to be able to play with them enough that you'll remember which one to look at. The first one, first pair that we're going to talk about is apoapsis and periapsis. Now, sometimes you'll hear this as apogee and perigee when it's around Earth, or apohelion and perihelion around the sun, and aparian and periarian around Mars. But these are the points. Apoapsis is the furthest away your orbit is from the primary body, and periapsis is the closest to the primary body. So what they do is when they're different, they define how different or how non-circular our orbits are. And when we have an open orbit, obviously the apoapsis is at infinity. Argument of perigee or periapsis, which is listed as omega, is the angle in the orbital plane between the line of nodes and the perigee and periapsis. So the line of nodes is the nodes of that orbit. So we'll show you some diagrams of that in a little bit. Another big one is conic section. All of our orbits are conic sections, from the simple circle through the ellipse, through the parabola and the hyperbola. And we're going to talk about those conic sections and a term called eccentricity, which we represent with E, which is how non-circular that conic section is. It opens when E equals 1. Anything less than 1 is a closed or elliptical orbit, and anything greater than 1 is a wide open parabolic orbit. The ecliptic is the plane in which the Earth orbits around the sun. Now, this is important because we use that when we look at orbits and transfers through the solar system. But we also use that when we relate stuff with the Earth-fixed, Earth-centered orbits that we have. Gravitational parameter, mu, is just g times the large mass, the gravitational well. It's how deep in the well we are. A big one that we're going to talk about, and something that's going to become very pertinent to all of the calculations you do in this unit, not necessarily next year, is an impulse burn. An impulse burn is a type of burn that provides all of the energy and momentum transfer in an instant. In reality, there's no such thing as an impulse burn. But for the purposes of this unit, most of our high thrust rockets, chemical rockets that we use on launch vehicles and large spacecraft, qualify as almost impulse in nature. And for the purposes of our simplified calculations, we can treat them as impulse. Now, if you had an electrical or low thrust propulsion system, millinewtons of thrust on a many kilogram spacecraft, you couldn't use impulse. You have to use different assumptions. Orbital inclination, or I, is the angle through the equator or the ecliptic. So if it's around the Earth, we use the equator. If it's around the sun, we use the ecliptic that the orbit passes. If it's 0, it's equatorial or ecliptic in nature. If it's 90 degrees, it's polar. Anything less than 90 degrees is what's called a prograde orbit. That means we're using the energy of the rotation of the Earth to move us around. If we're doing anything greater than 90 degrees or retrograde orbit, we've got to take all that energy and velocity out again. And it makes launches a lot more complex. And we'll talk about that in a few weeks when we talk about actually getting off the Earth and all of this stuff. We talked about periapsis. The next one is right ascension of the ascending node, or RAN, or omega. This is the location of the crossing of the equator or the ecliptic by the line of nodes with regards to the vernal equinox. So we tend to link everything to a specific reference point. And as we move around the Earth, we can find the point on the Earth where the ecliptic and the equator cross each other, and that's on the ascending, and that's the vernal equinox. On the descending is the autumnal equinox, and it basically equates to where in Earth's orbit and rotation that would be for the northern hemisphere spring for vernal and northern hemisphere autumn or fall for the autumnal. And it's just how far around we've gone. And that processes over time. Our solar day is the length between 2 consecutive solar noons, which is different from the sidereal day, which is the time it takes Earth to rotate 360 degrees. Now, I want you to think about why they're different. What is it about the way Earth behaves that produces a slight difference? And then I want you to think about which one is actually longer. And we can discuss that, but I'd like you to think about that before our question and answer session. We have semi-major and semi-minor axes. These are the long and short axes of the ellipse, respectively. Our true anomaly is the position of the satellite in orbit. It's defined as the angle between the satellite and its periapsis. So it's just where you are in your orbit, where in that line of nodes. And then, of course, the vernal equinox, which we already discussed. Okay, so to finish up this video, we're going to talk about some basic orbits, what we call going round and round, because our basic orbits are generally closed. They're the orbits we're most interested in. So to get there, we need to first talk about our reference frames. We have 2 primary reference frames that we use in space flight and orbital mechanics. One is the geocentric, that's Earth-centric reference frame. You can also have an aerocentric or Venusian-centric reference frame and a Jovian-centric reference frame around any body, but it's when we're orbiting the body of interest, be the Earth, the Moon, Mars. And there we have a vernal equinox, that's the classic one, our equator, which is the XY plane, and our axis of rotation, the Z. So that's just what it is. We can put all of our information in there in terms of omega, big omega, little omega, the line of nodes, all of that on there. When we're orbiting the sun, same thing happens, except for now, instead of the equator, we have the ecliptic. And as you notice, when we go from Earth to a heliocentric, from a geocentric to heliocentric, the planes change on their own. There's an inclination. Even a 0 inclination orbit around the Earth, once you escape and start orbiting the sun, will no longer be 0 inclination. But the same thing applies. It's just basically instead of the equator, we have the ecliptic. Okay. I want you to have this slide or some graph of this slide at hand for your midterm and your final exam, because it's very useful. And those functions and symbols are things that you should be able to remember you've written down, because we'll be using that. Okay, just remember that the equator is aligned 23.45 degrees to the ecliptic, and that's why we have our seasons on Earth. Okay. Let's talk more about those elements that we put in the definition. They're called Keplerian elements after Johannes Kepler. We have A, E, I, omega, omega, and V. A is the semi-major axis, E the eccentricity, V the true anomaly. I, the orbital inclination, and then of course the RAN of the ascending node, right ascension of the ascending node for big omega, and the argument of periapsis for little omega. And with those bits of information, you can define both the orbit itself and then ultimately exactly where the spacecraft or body is in the orbit at any instant in time. And also with all that information and a bit of information in precession, you can see how that orbit changes over time. So A, E, and I define the orbit, and then V, omega, and omega define where the spacecraft is in that orbit. So just that's what you need to remember, and you need to be able to work with those. And we're going to start working with those and doing simple calculations from here on. And then, of course, next year in space systems, you'll be doing much more sophisticated calculations, both by hand and using orbital analysis and mission analysis tools like GMAT and SDK and the like. Okay, our simplest orbit, the circle. We're going round and round and round. Our eccentricity is 0. Our A is equal to R. It's also equal to our semi-minor axis. And the key thing about this is that every point in an orbit, no matter where we are in the orbit, whether we're here, we're here, we're here, we're here, as long as this body is relatively uniform in density and diameter, our kinetic and potential energies are constant. They don't change. So the energy of the orbit is constant. That's the definition of an orbit. We have a constant overall energy, and the split between potential and kinetic energy doesn't change at all. So what's this about energy? Well, each orbit has a specific energy associated with it. And for a circular orbit and closed orbit, this specific energy, epsilon, is negative. It's minus mu over 2r. So the depth of the gravity well and how far away you are from that gravity well. So just how deep that gravity well is. And obviously, the further out you get, the closer this number gets to 0. It gets bigger effectively. And that's interesting because at some point, what will happen is you'll get far enough away that this effectively becomes 0. You're no longer in the sphere of influence of that body. And that's what we talk about when we talk about leaving Earth or leaving the solar system. We're leaving those spheres of influence. Okay. So we had that nice circular orbit. Let's go to that more general closed orbit, the basic ellipse. Again, energy is constant, but in this case, the split between potential and kinetic energy isn't constant. It changes at every point in the orbit. It gets higher kinetic energy towards your periapsis and lower kinetic energy towards your apoapsis. Again, eccentricity is now greater than 0. It's not strictly 0, but it's also strictly less than 1. And this covers almost all of our closed geocentric and heliocentric orbits. In fact, for most spacecraft, even if we're no longer closed in a geocentric point of view, we're still closed in a heliocentric point of view. Can you think of spacecraft that aren't closed in a heliocentric point of view? There's only a few of them. I think there's exactly 3 space probes and 3 upper stages that are not closed in a heliocentric point of view. Again, epsilon is minus mu over 2a. It's still negative, but as this orbit gets more and more eccentric and the a gets greater and greater, that energy gets closer to 0. So this is what we mean by negative energy. As long as the specific energy is negative, our orbit is closed. Okay. So let's take a quick aside on some geocentric orbits before we go on to the open orbits and the like. First one, low Earth orbit. And in fact, low Earth orbit is a class where we have several inside that. And those are typically around 100 to 2,000 kilometers above the surface of the Earth. Now, that's not the radius of the orbit, that's the altitude of the orbit. So the radius, you need to add the radius of the Earth to that. They're very short period. In the case of the orbit of the ISS, it's about 90 minutes, and some are even shorter, longer as you get further out. And we typically use these for 2 purposes: detailed observation, because you're close to the Earth, and also to put people in space, because it takes a lot of energy to get humans and all their life support somewhere. So we tend to operate a little bit lower than we would otherwise. And this is especially true of the International Space Station, whose orbit is determined by the payload capacity and lift capacity of the Soyuz and Progress systems. If it had just been the space shuttle, the inclination would have been less and the orbit would have been higher, but it's that compromise. Above that, we have a class of orbits called medium Earth orbits. These are 2,000 to 3,000 kilometers above the Earth. We get greater coverage for any one satellite. So it's really useful for things where we don't need really, really high resolution or high bandwidth, but we want reasonable coverage and we want lots of satellites across a lot of things. Think GPS, for instance. That's a classic medium Earth orbit satellite. You get more time on station, so they're visible for longer, and you get a lot less drag. Now, remember the question about the atmosphere. Yes, there still is an atmosphere in these places, and it degrades over time, but the lower your orbit, the more drag, the more losses you get. In fact, for the International Space Station, it's about a nautical mile of orbit every month if you don't do anything. Above that, we have our geosynchronous and geostationary orbits. And the only difference between these two is the inclination. Geosynchronous means you just orbit the Earth every 24 hours. And that's one orbit that provides that. If we drop the inclination to basically zero, we will stay above the same spot on the Earth at all times. And we use those for things like communication satellites or satellites where we need to be in a specific place every time and know where it is. We've got some more eccentric orbits or different orbits that are really, really common. They have different altitudes. They may be low, they may be medium, maybe geosynchronous. First one is sun synchronous orbit. And the purpose of the sun synchronous orbit is so that we pass over the same point on Earth at the same point in the solar day every time we revisit. And that means we get consistent relative to the seasons lighting of that spot. This is a retrograde orbit. Our inclination is greater than 90 degrees. It's 98 degrees, which means, of course, we have to put a lot of energy into it. So it's something that we don't want to do unless it's really useful. And we use this for Earth observation. So whether that be weather satellites or spy satellites or the like, we tend to use these sun synchronous or retrograde orbits. The Molniya orbit is a really interesting orbit, and it was primarily used by the Russians and the Soviets before them. And the reason why is it gives you a great 24-hour period. The satellite orbits the Earth once every day, and you get long dwell times up at the apogee. So you have a huge vision of a spot in space over a long time, or a spot on the Earth over a long time. Obviously, your dwell time at the perigee is much, much less, so it quickly goes around that. But the really nice thing about these orbits is I can visit the spot every time in the same day, and I can have really high inclinations at those spots. So I can cover much more of the Earth than a standard geostationary communication satellite. And this was important to the Russians and the Soviets because so much of their area they were operating, especially militarily, was in the Arctic. And the thing about geostationary satellites is they're really not visible from above about 75, 78 degrees north. So you needed something where you could communicate. So that's why they use those orbits and those satellites. Okay. In the next video, we're going to talk about open orbits and orbit transfers. So thank you for joining us, and I'll see you there.